So the next talk will be by Vita, and Vita led the development of a stock trading platform, which was mostly based on Python, with some C++ and Python sprinkled in. And at that time, he learned about scaling and performance in Python. Yes, and this became a passion for him. And now we're looking forward to hear about the notorious guild, or chill, or however you pronounce it, the global interpreter lock, and how Python 3.13 changed the game or will change the game. So an applause for him and welcome. Thank you.
Hi, everyone. My name is Vita, and I currently work as a freelancer and consultant, and I specialize on performance, mostly of Python applications and distributed systems. This is because I've got background in finance and trading, where it was important for us to process a lot of data fairly fast. So we used async I/O and threading and multiprocessing, all that stuff. And I also do some machine learning for this nonprofit project that aims to digitize the consultations procedure for new laws in Switzerland. I'm going to start with a story. This should be a familiar number for many of you. So when I was a high school student, some 18 years ago or so, I had this project in C++. It was a system for distributed computing. And my goal at that time was to calculate the Euler's number, which is what you're seeing there, to 300,000 decimal places. So I wrote a C++ program for that, and the school lent me a classroom of computers during spring break, and the computers spent most of that week calculating those 300,000 digits. And it worked out. I won some student competitions with that, and I thought it was pretty cool. And this is what I ran yesterday morning on my laptop with the new Python 3.13 with the GIL removed. And it's a single Python process utilizing all cores on my laptop and taking 28 seconds to calculate the same thing. And it is terrible. Like, you would never want to do this in Python first. Second, the algorithm is not great for parallelism. There is no optimizations. It's just the most trivial thing you can do. And of course, even single-threaded, it would be faster than 1 week 18 years ago. But still, it felt pretty cool to do this in Python with 10 threads. What I'm going to talk about, subinterpreters and free threading, is a field that currently developing very quickly. A lot of things change from week to week. So there's a lot of excitement in the community and among Python core developers about these things. There's momentum, so problems get solved day after day or maybe week after week, and we get new features and a lot of progress. But all of that is generating some confusion as well, because it's sometimes difficult to find out how these things work, what's actually included in Python, and where the documentation is. So my goal with this talk is to synthesize a few sources and give you pointers so you can follow them on your own and try these things yourself. There will be a lot of links and references in the presentation, so I encourage you to just download the slides afterwards so you don't have to take photos. And I will be simplifying a lot of things, so I apologize in advance if it sounds sometimes too simple, but I'm trying to make it understandable. Many of you have heard this 1,000 times before, so I will be brief. Why do we have the global interpreter lock? What is it good for? First, it's good to differentiate between Python, which is the language that we all like and use all the time, and CPython, which is an implementation of the interpreter for the language. And most of us probably use CPython, but it's not a rule. So I just want to make this clear. And this talk is really only about CPython. CPython is written in the C programming language. And likewise, we have a lot of extensions for Python that are also written in C or sometimes Rust, C++. And the GIL is intimately related to memory management for Python objects. So every time you create a variable, an instance of a class, or your function ends and the variables go out of scope, all of that needs to be handled by the interpreter, allocating memory for you and then freeing it when it's not needed. And the GIL exists in CPython because it simplifies a memory management technique that's called reference counting. And the lock is used by the interpreter to safely calculate which of your memory regions are still in use and which memory can be already discarded. Getting this wrong results either in memory leaks in the better case. In the worst case, it results in hard crashes of programs. So the memory management is a crucial thing, crucial feature of the interpreter. And the GIL makes it easy to do it. But the GIL also has a side effect. While it exists, we cannot get, almost never can we get true parallelism in CPython. And that also means that a lot of possible bugs that exist in parallel programs cannot yet exist with the software that you're using in many extensions and our code. So while the GIL exists, it's somewhat easier to reason about code, and especially C code. So the first concept that may maybe not rid us of the GIL, but make it less problematic are subinterpreters. It is a concept of having multiple Python interpreters running in the same process. And each of these interpreters would have its own GIL. So it wouldn't be a global interpreter lock anymore, or less than global. And in each of these interpreters, you can have multiple threads, and those threads will still be throttled or limited, restricted by the GIL of that interpreter. But if you can have multiple interpreters in the same process, you can have multiple threads running in parallel. And in theory, there is still some shared memory between all these interpreters because they're running in the same process. So theoretically, this could be superior to just using multiprocessing, where you run one Python interpreter per process. And this is not just a concept, it's something you can already do in Python 3.13. This is one of several ways how you can execute code in a different interpreter. It's a bit surprising, or it's a strange situation, actually. And how we got here is not, it's a bit difficult to trace. Last year, Python 3.12 gained an important feature. And for the first time ever, we actually got the ability to have more than one GIL in a Python process. This was merged last year and already was in Python 3.12. The idea of having multiple interpreters exists in Python since 1997. But until last year, there would still just be one GIL for all of them. So this was an important obstacle that was removed. Meanwhile, there was a very long discussion that was taking place over 6 years about making making that diagram I've just shown you possible, having more than one interpreter in a Python process and making that available to users to call and use. And that wasn't ultimately accepted, but that's only because it was replaced by a fresher document, because after those 6 years, there was so much discussion and opinions that the developers decided to just simplify it and start fresh. And you will notice there is no end date in Python version because it's still not officially accepted or implemented in Python. So how come I've just shown you a code sample? I took this screenshot 3 weeks ago. Eric Snow is the main person responsible for Subinterpreters. And 3 weeks ago, he himself wasn't sure what the future was going to be about the Subinterpreters. And in this discussion that I'm linking, as far as I know, it's pretty much the only place where you will find the resolution that Subinterpreters are going ahead and will be officially implemented. So at the moment, they are implemented unofficially. So like I said, the proposal is not accepted or implemented, but it actually is implemented. At least a part of it already exists in CPython, and you can use that. It does not exactly fit what's written in the PEP. The APIs are different. So when I was playing with this, I just had to read the CPython code to figure out how to use subinterpreters, which sounds crazy, but it works. And I'll show you some real-life examples of this working. So in the beginning, I mentioned shared memory between subinterpreters as a potential differentiator compared to multiprocessing. There is a concept of queues and channels, which it is not a new concept, it's just applied to subinterpreters. And these are mechanisms to send messages between subinterpreters, just like you would communicate between multiple processes. But because there's shared memory, there are actually already some optimizations in place, so you can share immutable objects between subinterpreters, and you don't have to pickle them or copy them. So that's very nice. As things stand right now, a lot of things like anything mutable that you would want to share between subinterpreters would have to still be pickled and copied, but the communication will still be faster than between processes because it is within the same process with the shared memory. I wanted to build a demo for this talk, but then I found that other people have built better demos already. So I'm going to share this excellent talk from this year's PyCon US by Anthony Shaw, where he's using subinterpreters to implement a web server. And as new requests come in, they are handled by multiple subinterpreters. So you can have essentially a multi-threaded Python program where in each thread there's a separate interpreter running and handling the request. And the way this works is that the subinterpreters handle various sockets or file descriptors of the same process. There are some links for you to follow if you're interested in this. Another interesting concept about, or another interesting approach to sharing data between subinterpreters dates back to some computer science ideas from the 60s that were, of course, developed further over the decades, but very cool data structures that Yuri Selivanov is using in another PyCon US talk to basically implement not zero copy, but data structure sharing that almost doesn't have to copy any data between the subinterpreters, and you can still have something like a mutable dictionary between them. It is a very experimental project on GitHub. I'm not sure he's still developing it, and there's no documentation. But I think this idea has real chance to take off. It's not simple to implement, but it's when it works, and it seems to work, it's very efficient for this kind of data sharing. So to summarize, some potential ways how you can use subinterpreters. You can just have them talking via those queues or channels. You can already do that. Again, it's not easy to find where to import these things from. So at the end, I'll give you a link to these slides. And on that link, you will find an example how to actually import the queues, because it's not even clear where they are, but they work. So this is similar to multiprocessing, but more efficient because you have one process and the communication is more efficient than talking via some interprocess communication mechanisms. Or you could have something like Anthony Shaw is doing, where the subinterpreters don't even need to talk to each other that much because they have divided the file descriptors of the process that they are handling. It's like having multiple sockets open and serving requests on them. Or there is the tantalizing idea of figuring out a very smart mechanism of sharing data between the subinterpreters. For example, what I've shown you with Yuri Selivanov and his MemHive project. So this is slightly more difficult to do, but I've got some experience with high-performance trading systems, and their shared memory is always the way to go for the most efficient communication, even between multiple processes. So I think this would be the ideal solution or class of solutions. There is a problem with subinterpreters, and that is that not all C extensions support them automatically out of the box. Some of them need to be adapted to really work with subinterpreters. And the reasons for that, I'll come back to those when I will talk about free threading, because they're actually related. And it's because the GIL, like I said, made it convenient for us to write software because we couldn't get a lot of bugs with parallel code. So some extensions, in the good case, some extensions will refuse to be imported in a subinterpreter, and you will get an import error. Some extensions which have not been adapted at all might crash your program. So this is NumPy, for example, being imported in a subinterpreter, which is very unfortunate. But I believe this will get fixed. It will just take time. So if you're interested in some of these packages, I've also linked issues tracking these. I should mention that if you only use Python code, then you won't have problems. You can import anything in subinterpreters. Now on to the innovation that's probably more known than subinterpreters. And this is very new. In Python 3.13 that was released last week, we now have something called the optional global interpreter lock. And the route there seems much simpler than with subinterpreters. It's just one path that was accepted, merged, and that is it. In practice, it wasn't that easy. There were so many failed attempts and projects to remove the GIL before from CPython. And maybe they paved the way. They researched some possible avenues, but they never quite succeeded. So how come we can have this now? I really recommend reading the whole document. It's quite accessible, and I think it's a great example of very pragmatic engineering that solves real-life problems. And it has interesting ideas in it. And the first one is reworking reference counting, which is the memory management mechanism that I mentioned in the beginning. And that is by observing that even in multi-threaded applications, most of the memory, most of the variables you have are only ever touched by the thread that created them. So the observation is that most of the memory you have can behave kind of like in a single-threaded setting. And multi-threaded access to the same memory is an exception. So the reference counting in this optional GIL Python is different. It's called something like biased reference counting and deferred reference counting. For details, I really recommend reading the document. Memory management was reworked as a whole in CPython. So the developers replaced the whole memory allocator for the entire Python interpreter, which is a pretty big deal. And also garbage collection, which is another mechanism of memory management for CPython, was reworked. A lot of these changes basically need to solve the technical debt of having relied on the global log always being available, and it was perfectly fine for a lot of code to just hold the log to do its thing. Now, when the log isn't there, the code needs to be a bit more careful and smarter. And another example of that is when you have objects containing other objects, like lists or dictionaries, they now, each one of them has its own log instead of there being one global log. So every single list and dictionary you create now uses its own log for safe access to that container. So I've just summarized the ideas in a few minutes. There's a document you can read in an hour, probably. Why could not we do this sooner? Why now? There's always been problems around reworking reference counting, because if you don't have that global log and you have a lot of smaller logs, then that generates a lot of overhead around that. And this isn't completely solved yet. So this new Python 3.13, without the GIL, if you run it in a single-threaded scenario, it will be slightly slower than the normal Python. There is reasonable hope that this, maybe not hope, there's reasonable expectation that this will be solved over time. But if you're only ever running single-threaded and performance is an issue, it's better to just stick with the GIL for now. And the other big problem that's always hindered the removal of the GIL was making C extensions compatible, making them work with the absence or with the fact that the GIL is no longer available. And again, that's not completely solved yet. So many C extensions cannot be imported in this GIL-free Python. Or if they are imported, they will force the interpreter to re-enable the lock at runtime. So I've been talking about the normal Python and the GIL-free Python. That's because for the first time, we now have two different builds for the same Python version. So Python 3.13 is the same old, well, it's a new version, but it's still the Python as we know it with the GIL in place. Nothing has really changed about the GIL there. And then we have Python 3.13t, which is a separate build where the GIL is optional. Optional means it can be re-enabled at runtime. And this is to make the possible removal of the GIL more manageable, because completely changing the Python build for everybody and removing the GIL would be an extreme breakage, would be an extreme change, probably worse than we had between Python 2 and 3. So to make this even possible to experiment with GIL removal, we now have two builds. And it is an experiment, and there is a possible future where the experiment will be abandoned, and maybe we will be stuck with the GIL or somebody comes up with a different solution. But of course, the ideal outcome that core developers are hoping for is that the issues with compatibility and speed of this GIL-free Python will be solved over some years probably. And eventually we will just have one Python without the GIL. How can you try this? If you use pyenv, in the past week or so, it's become very easy to install this GIL-free Python. So if you use pyenv, it's just 2 commands away. And then when you run this special Python, it tells you it's the experimental free threading build. Since Tuesday, I believe it's become possible, if you use UV, it's become possible to get this GIL-free Python. And if you use a graphical installer, both for Mac and Windows, there's just a checkbox that you check, and you can get it. There is, unfortunately, a similar catch as with the subinterpreters, which I believe I've mentioned. The extensions need to be specifically built for this GIL-free Python. And extensions can request the interpreter to re-enable the GIL, which is perhaps surprising, but I believe it's to make this whole transition and this whole experiment more manageable. Again, purely Python code runs without any problems. You won't get any crashes or anything like that. So this talk is called Subinterpreters and Free Threading in Practice, and I've told you cannot import a lot of stuff. I was myself a bit frustrated by this, figuring out what I can and cannot use, what causes a crash, and so on. So I've built a compatibility tracker. So I've built a script that tries to install the first few hundred most popular packages for Python from PyPI in isolated environments with either the GIL-free Python or normal Python, but using a subinterpreter. And I've generated this table where you can look for the extensions you would like to use, and you can check if they are already compatible or not. So if you're interested in trying these new things, you can check the tracker at parallel.python.tips. You will notice when you scroll through the table, you will notice that there is actually a lot of green color. So a lot of stuff can already be used. It's not all doom and gloom. Just to quickly summarize why we need to do so much work to make extensions compatible. It all has to do with the fact that it was convenient to have the GIL, and a lot of code that was written in the past isn't actually thread safe. So now when we remove the protective function of the GIL, a lot of code needs to be fixed, actually. It's about fixing parallel bugs. And the GIL has allowed us to commit them for a long time. But writing truly parallel code is actually very hard. I've written a lot of thread unsafe code myself, so I would know. And this is just a natural evolution, I believe, in the Python ecosystem. I remain an optimist about this because we now have a great combination of kind of being able to imagine how the GIL can be circumvented or removed. We have strong motivation because we have a lot of CPU cores everywhere. We do want parallel computing. There's momentum. Actual things are getting solved and shipped. And excitement because it seems we will really be able to solve this. I believe for the first time, there's like a viable path to remove this problem. And since I already have parallel Python running on my computer, I asked it to print this slide in parallel for speedups, of course. And I got this. So I think a new era begins where we will be fixing all our race conditions and thread unsafe code. Thank you for listening to me, and I'm happy to take questions.
Thanks a lot for that interesting insight. Are there questions in the audience already? Do we one hand there on the right?
Hello.
Okay, this one works? Okay.
No, hi.
You win.
Thank you for your talk. And how long does it take you for calculating the Euler number now without the GIL?
Without the GIL, the example I showed at the beginning, about 28 seconds or so on my laptop.
Okay, I thought it was with. Thanks.
But I want to emphasize, I'm not proud of that code. It's not optimized at all.
All right. The mic working?
Yes. Thank you also for this really interesting talk. About your table with the green text, is it just loading without an exception, or is it guaranteed to be thread safe?
Very good question. It's absolutely not guaranteed to be thread safe. It's just the first hurdle of being able to install it, which is not guaranteed, and then being able to import it. And for the GIL-free Python, the free threading Python, if an extension is imported and it doesn't explicitly say it is safe to run without the GIL, then the interpreter re-enables the GIL. So the table, the tracker, actually checks that you can import it and the GIL remains disabled, which means that the extension claims it is thread safe.
Okay, thank you.
Okay. There's a further question right there.
I just lost a race condition asking you about the Euler function. So, and do you have that as a sample of also on your slide? I mean, on your reference to run some Hello World?
Do you mean the Euler calculation?
Yes.
I have not uploaded that, but I can do so. It's, I don't know, 50 lines of code. It's a Taylor expansion of the constant. It's a very simple code. I was going to show some sample code for the free threaded Python, but it just looks the same. Nothing has really changed there. You just use a different interpreter, but the code, which perhaps uses threads, now suddenly can use them really, which wasn't possible before. I mean, you were using threads, but they were not really parallel.
Okay, are there further questions? Oh, over there on the right.
Hi, thanks a lot. That's really, really useful. I just want to clarify with you about threads. So when you talk about threads, you mean that when we create a sub interpreter, there are really operation system threads involved, right? So it's like a multi-threading, but now we're not blocked by GIL. So we use the operation system threads here.
Yes, that has actually always been the case with Python. We were using operating system threads. They were not some runtime invention of the interpreter. But the threads would very often need to acquire the lock. So even though they were real operating system threads, they would be blocking quite often. And that hasn't, I mean, we are still using real threads, but now they don't have to block.
Okay, thanks.
All right. We would have time for one final good question. If there isn't any hand raised, then I think thank you a lot for your
Thank you.
time and talk.